And today, what I would like to share with you is research that was conducted in cohort with my PhD student, Mr. Bhaskar Botcha. He is finishing his PhD. And along with his work, this talk will touch upon the works of my recent graduates, Zimo Wang, who is currently on the faculty in SUNY, Binghamton, and Asif Iqbal, who is now on the faculty in the Arizona State. And also all three of them, Bhaskar, Zimo, and Asif, they were mentoring students from IIT Tirupati when the students were there as interns. So some of the papers I will be presenting would be co-authored by students and some faculty from IIT Tirupati, and I would like to acknowledge as I mentioned them. And this talk essentially is based on some of our recent works. And my talk will begin by introducing smart manufacturing, just to establish a common terminology with which we can proceed. And then we'll go into basically a slew of works that has been done in the last 2 to 3 years. The first one will touch upon the architecting of this smart manufacturing machine tool with which we could conduct some of the things that I had mentioned as part of the topic. And through this process, I will introduce the idea of material on demand manufacturing, as well as what is AI-driven characterization and process monitoring. And also we will get into the details of some of these methodologies. At that point, Bhaskar will take over and then give those details to us. So the overall presentation will involve virtually 2 parts. My initial introduction hopefully will set the stage for understanding the nuances of some of the technical details that Bhaskar would present. So let me begin by introducing what I think of when I talk about smart manufacturing. Um, Smart manufacturing, as many of us probably can relate to, is the next generation of manufacturing. And of course, it imbibes the advances in AI and data science, advances in materials, and also sensing, communication, advances in energy and computation, and the latest communication electronics. And of course, it is an advancement in the manufacturing technologies in particular, including additive, hybrid, and so on. So confluence of all these 7 different technological advancements constitutes what we can think of as smart manufacturing. And currently, Texas A&M has a very active research portfolio in smart manufacturing. What you're seeing are the 5 projects that we are currently undertaking, just our group is undertaking in this area. And today's talk would be based on the things that we are doing in the first 2 projects. The first one being in the development of this hybrid 3D printer. And second is leveraging the capabilities of this printer for autonomous materials discovery and material on demand manufacture. So to set the stage once again, when we think about smart manufacturing, of course, we bring all these technologies together. The immediate question is, so what? Essentially, it leads to 2 very interesting possibilities. The first possibility is transformation of manufacturing into a service. So essentially, we can, it's basically like a Uber for manufacturing, right? So the idea is today, whenever you want to have any custom part made, so you basically reach out to a supplier, and the supplier has to make, and they usually take a few weeks before they make it and then ship it back. That's because the entire IP or the intelligence is completely concentrated. But with advancement in smart manufacturing, manufacturing as they speak is going to get democratized. So in other words, you can actually push the high IP content to your local manufacturer so that you can actually not only deliver the item, but also make the item at the point of need. Everybody is familiar with the models of Amazons and so on, right? What Amazon can do is it can deliver things on demand. It's still not able to make things on demand. They are working on it. And what will enable such make on demand capability is smart manufacturing. How will it, what kind of technological advancement can lead to that? We will see as we get into the details of this talk. But first one for us to remember is smart manufacturing can transform manufacturing into a service. Second transformation that can take place because of smart manufacturing is the idea of materials on demand manufacturing. The idea here is the whole idea of the customer getting the needs fulfilled by being able to manufacture on the fly. But this process, if you go deeper, essentially involves taking the customer needs and converting them into functional requirements, clear specifications, and translating the functional requirements into clear design specifications. If you think of design specification, the first thing that comes to our mind is basically the geometric shape that can be accomplished through the use of appropriate CAD drawing. That will be the outcome. And similarly, you can actually specify the morphology, the kinds of things that you want to have on the surface and so on. And the third, microstructure and the material composition. So in essence, the entire process of design essentially involves specifying the shape, morphology, microstructure, and material composition. Currently, in most of the engineering practice, by and large, the microstructure and material composition are pre-decided. We only select them. And most of the engineering design involves generating the shape and to an extent morphology through the use of manufacturing processes. Again, let me repeat. Current design practice essentially involves generating the geometric shape and morphology and just selecting the material. The transformation that we are looking at is we are moving from just selecting the material to actually designing the material and tailoring the material for the application we are looking at. So you're creating material on demand, just like you're creating the shape on demand. Please remember that. So this is a new possibility that's emerging. Why is it important? If you look at many of these advanced applications, they are all becoming possible because of the material tailored to an application. What you're seeing here is basically a morphing wing of the next generation aircraft. And this whole wing of the aircraft is a single piece, except that some parts of this aircraft have a special shape memory alloy material tailored to create that kind of an actuation. And similarly, you can look at 3D printed homes. You can look at the next generation of complex concrete, whereby you can actually endow the right kind of property at the right location so that it behaves appropriately for this whole construction. And even at the consumer level, you can actually create integral components, integral custom components. Like you go to your doctor or optician, you get your specifications, and as soon as that's done, it will be digitally printed. Again, a single piece, but different materials put together. So the whole idea that's getting transformed is you're actually designing the material to go with the specification. And it's highly personalized, and you can enhance the functionality like you have not seen before. And you can actually put, quote unquote, multiple materials, quilt them together to make your product. And that can lead to a lot of advantages, especially for people who are conscious about the environment, very frugal, minimal material wastage, and also optimized for energy. So there are lots of interesting possibilities will emerge through the use of this material on demand paradigm. And how can we enable it? Do we need a new kind of a machine whereby you can actually enable both this manufacturing as a service as well as material on demand? One way in which it can be done is through the use of what we are working on is a smart additive or hybrid machine tool. I will get into the overview of this through the video. And I will let Bhaskar take over after the video to describe the nuances of how this hybrid machine is constructed, and how we can actually use this hybrid machine to enable the material on demand manufacturing, and how can we tackle some of the technical challenges related to materials characterization that will occur in this paradigm of materials on demand manufacturing. So please give it a listen, and let me momentarily stop sharing and start sharing the screen again, because I forgot to do a particular step I'm supposed to do. Bhaskar, would you be able to share the screen from your end for that video?
Yes, sir, I can do that.
Yeah, please do. Because it was not letting me work on the audio.
Okay, no problem.
And again, as we present, feel free to ask questions through the chat line. Since one of us will not be presenting, we would be glad to answer as the questions arise. Thank you.
Yes, thanks.
Autonomous materials discovery is a challenge for current machinery. The research is an important step toward practical and fast material discovery. The smart hybrid machine combines additive manufacturing and machining. It uses lasers, metal powders, and heat treatment to modify the structure and properties of the created materials while collecting data about the material. This process can be automatically controlled using a computer. The computer uses code to create parts that can be simulated and verified by the machine before printing begins. The synchronous use of a high-speed camera and other instruments allows for faster data collection, which will speed up the discoveries of material properties. Around 1 gigabyte of data is generated every minute by the machine. This data, along with the discoveries from the machine, are speeding up materials discovery for the future.
Yeah, that was Bhaskar from 2 years ago. And Bhaskar, can you continue with describing this machine in full detail?
Yes, sir, sure. Thanks. Yeah, for those of you who are wondering why I don't look the same, that was before the pandemic. And Dr. Bukkapatnam, thanks for giving the very high-level introduction for smart manufacturing and the two facets of it, like how we are discussing the manufacturing as a service and also for the material on-demand manufacturing. So in the further slides, which I'm going to discuss, so we are going to get into the intricacies of this hybrid machine tool, which is being central to these two concepts, which we're discussing. So let me start off by giving the capabilities of the hybrid machine tool, which we were discussing about. So the first thing is the finished capabilities, which I'm going to discuss. So as we know, additively manufactured products, when they just come out of the machine, they don't have a very good surface. So they are printed layer by layer, and the material is accrued together by like melting of metallic powders. And obviously, when it comes out, the printed surface doesn't have a very good finish. With this concept of this hybrid machine tool, where we have the additive and subtractive modes of the machine built into the same machine, what we can do is we can print the surface, and without removing the part, like those of you who are in manufacturing, we know like how much of a time it just gets wasted when we are transferring these parts from machine to machine. If we are printing, then if we have to mill the surface and level the surface off, then we have to take it to the grinding machine and polisher. So all these steps using this novel attachment of like the subtractive part of the machine tool, we can do it all in the same machine. And we have actually demonstrated in this particular manufacturing letters paper that we can reduce the cycle times of the overall process by up to 40%. So what we can get from this is the samples are ready for characterization studies all in a single machine. So if we are aware of these characterization process, like if we have to go into nano indentation and find the hardness, nano hardness of some particular material which we have just printed with our particular composition. So to get that particular part ready for characterization, it takes like multiple machines and like multiple processes to get there. And with this particular setup of this hybrid machine tool, in less than 3 hours, we can go from fabricating a 3D printed component using directed energy deposition to a sub-micron finish, which is ready for characterization all in the same machine. So that's the finishing capabilities of this particular hybrid machine tool. And also, because of its unique construction where we can finish the surface, and also we can summon the laser again, and we can see how we can use the heat input from the laser to actually soften the material. So we are all aware of heat treatment. Rather than heat treatment, as Dr. Bukkapatnam mentioned, like this particular machine can be used to change the microstructure, as well as we are also the concept of laser assisted machining, where a very small laser is just used before cutting to soften the material so that we can prolong the tool life. So we can use this particular construction also allows us to use these thermodynamic pathways and use of the energy from this laser in situ heat treatment to manipulate the microstructures, as well as lower the cutting forces to help prolong the tool life. So that is one more advantage of this hybrid machine tool. So I'm just building on this particular hybrid machine tool concept, and we'll build around a sensorized hybrid machine tool around this and see how it can be used for our characterization purposes. So the next concept is the sensor fusion. So in this particular machine tool, what we have done is we have sensorized this hybrid machine tool. We have a force sensor, we have an acoustic emission sensor, and an accelerometer, and all these can collect data simultaneously. And each of these sensors can go up to acquisition rates of up to 1 megahertz. That is like 1 mega samples per second. So, and also one very good thing about collecting all these data simultaneously is, as we see in the further parts of the slide, we have what is called spatiotemporal resolution, which will enable us to go back and look where the process has gone wrong. So in the further parts of the slide, when I'm discussing about the case studies, it will be evident as to how the spatiotemporal resolution and collecting data synchronously is actually helping us to go back and look at what actually happened in the process. So, and this particular example here, we are just showing the synchronous acquisition of this streaming data. So during in the further slides, we'll also be looking at some milling data. So here you can see as soon as the machine tool has started moving, the laser head has started moving, we can observe a spike in the acoustic acceleration and forces. And because the printing process doesn't impart a lot of forces on the bed, we don't see a visible change in the forces, but definitely we are capturing some signatures which can be used further for analysis. And this video stream which you're seeing, that is also a sensor. This is a high-speed camera which can go until like 300,000 frames per second. This particular video is being captured at 1,000 frames per second. So we also use this particular high-speed camera along with some lens to just capture the infrared region of the spectrum, so that we can do some spatter tracking and actually see where these metal particles are flying off, and which actually has significant effect on the final quality of the part which we are printing. So now I've discussed with you about the capabilities of this hybrid machine tool and the advantages of sensorization and simultaneously collecting the data. So the first application which Dr. Bukkapatnam mentioned, the manufacturing as a service. But the second application where we're talking about material on-demand manufacturing and tailoring the microstructures and tailoring the material properties as and when it's demanded. Like suppose so the concept is to synthesize material with all these tailored properties on demand. So what do we need for this? What do we need for tailoring these material properties on demand? So we have the smart hybrid platform, which I've mentioned, with all these data streams. And next, so consider this this particular system, like the hands and legs of the body, like whatever movements which we make. And we have to map it to we should have a sensor fusion methodology and a PSPP, process structure and performance mapping. And through this, like consider this like the nervous system, which enables all these movements, the nervous system and the muscles which are enabling these movements. And on top of it, we need the brain, which is the on-demand material synthesis control brain, wherein if I suppose the brain gets an input as to like I want these particular tailored material properties, we can go back, send the inputs to the machine, and again using these sensor fusion and PSPP mapping can actually go back and give the exact parameters so that like we can tailor like whatever properties are required, we can input it to the machine and get the properties out. So we see that there is a forward mapping which helps us understand this is the process understanding, and this is synthesizing the material, which is the reverse mapping, which is going back. So now the concept of autonomous materials discovery, we discuss this as a bottleneck and an opportunity. So right now we have data, we have many machine learning models which can be applied to the data. So and as I've mentioned, like we have the capability of collecting data up to like 1 mega samples per second. And we also have models which can pre-process and post-process this data and give us inferences if we know the ground truth. And the next part is actually finding out the ground truth, which is the most difficult part in manufacturing experiments. So we have the experiments and we have the testing and instruments and etc., which can help us discern what the properties of the particular part which we have done the experiment on. And the critical part here is testing, analyzing, and characterization of these parts. So characterization is the major bottleneck, as discussed in this 2018 paper. So what happens is if we are looking at tailored microstructures, so if I go ahead and print a part, and if I need to know the material properties right then and there, like it gets difficult because the process itself, as I've mentioned, involves like multiple machines and shifting the path through multiple machines and getting the characterization done. So that is the bottleneck. But the opportunity where we see is like, can all these three, the testing, the experimentation, testing, and analysis and characterization, this particular cycle, can this happen simultaneously? So that's the question we would like to answer. So from the testing, analysis, characterization, and experiments, we can collect the data. But can this happen in a loop? Can we get the material properties at the point of where the experimentation is actually happening? And can we tailor it to our needs? So that is one opportunity which we see, and that is a very lucrative opportunity which the smart additive manufacturing and hybrid manufacturing platforms actually offer. So because the experimentation we see as fabrication, like printing the actual part, but the testing, analysis, and characterization, can we add some mods to this particular hybrid manufacturing machine tool and get this done within the machine itself? So that's the whole idea. So let's start. So to demonstrate this, let's start with a few case studies. Like this is the basic characterization route, the characterization using nano indentations and nanolithography. Why I started with this particular case study is this is the basic form. I wouldn't say basic form, the traditional form of characterizing a material. So I print a part, I kind of polish the surface, make it ready for characterization. I etch it, I find out the microstructures, then go take it to a nano indenter, make some nano indents at wherever I see or expect property differences, and see if that is what actually happened. So this is kind of giving me the ground truth as to what the actual hardness values are. But as I mentioned earlier, it takes multiple steps. So this particular sample is a Ti64 sample, and it has these different phases, alpha and beta. So alpha occupies around 90% of the phase of this Ti64 matrix, and beta phase around like 10%. And what we wanted to see was this is a nano indentation setup, and the the premise is this: we use the nano indenter and make a nano scratch on the surface. And there are, if you see this, this is again instrumented like our smart hybrid machine tool which we saw. So there is an accelerometer near the indenter, and there is an acoustic emission sensor which is put right on top of the Ti-64 sample. And this is the nanolithography head, which approaches the material and kind of makes a very tiny nano scratch on the surface. And we are still capturing the data at 1 mega samples per second. And these two are the different signals which you see. This is the standard microstructure. This is the signal when we are scratching the standard microstructure. And this is the signal when we are scratching a diffused microstructure. In the next slide, I'll show like how these two different microstructures look. So this is the standard microstructure where we have the different compositions of alpha and beta. And this is kind of an effect of the polishing, which we have like the effect of a diffused microstructure, more like you can see these beta phases placed more like flat sheets or planes. So we have made 5 scratches here on this standard microstructure and 5 scratches on these diffused microstructure. And we have collected the data from both these scratches, both these nano scratches. And we are seeing if we can characterize or we can classify these two, because these two stand apart in terms of the signal features which we are looking as we'll be looking in the further slides. So we are trying to train a machine learning model and see if these two actually stand apart. And by just doing this experiment, if we can discern the properties of the microstructure. So these are the signals from from the standard and diffused microstructure. And what we did is we just took a fast Fourier transform. We just took an FFT of this particular signal, and we have divided the whole FFT into like multiple bands. So we say like the bin size is around 20 hertz, and we find the total energy of this particular frequency spectra in the 20 hertz. So if the concept of binning is new, like I'll be discussing that in detail in the second case study, where I have done some where we discuss rapid characterization. So for now, just take that we have divided the frequency spectrum into 20 hertz bins, and we have used those as features. So now I know the ground truth because I've used a nano indenter already. So the ground truth is I know that this is a diffused microstructure and this is the standard microstructure. And we have a set of, we have a feature set which is emerging from this particular signal. And we use the features to train a random forest classifier, a basic random forest classifier. And if we extract the important features, so random forest classifier has this really interesting way of defining what features have contributed best to classify these two microstructures apart, or these two classes apart the best. So when we looked at the most important features which are actually helping us to identify these two microstructures, the first one is the 0.3 to 1 kilohertz, and the next one is 30 to 50 kilohertz. And this particular plot shows the value of importance versus all these different samples where the scratching has happened. And we can clearly see that with the naked eye, we can just clearly see that we can clearly draw a line and say that, anything falling above this particular area belongs to standard microstructure, and anything here is the diffused microstructure. So here, this particular, the diffused 5 is actually somewhere really close to a scratch, which is already on the surface. So we also see that not just from the microstructure, we also get from feedback from the lithography process itself, or how the surface is. So this particular thing is the diffused microstructure, which is kind of closer towards the standard microstructure, but that is what we get from experiments. So this particular process, again, let's ask the question, like, can it be faster? By faster, what I mean is, again, as I said, this is a traditional way of characterization and a traditional way of finding out the properties of the particular material, like the nano hardness values. but can it be faster, and how can it be faster? So that's where our experiments and where we are using this particular hybrid machine tool comes in. So this is the hybrid machine tool, and the concept is simple. So we brought this particular part, which has been fabricated in the machine itself, to a submicron finish. And what we do is, in a nanolithography experiment, we have a static tool which has scratched the surface, and we could see that we could find discernible features which can say if it is microstructure 1 or microstructure 2. So what we are doing here is we have a dynamic tool. This particular tool here is a micromilling tool. It has, the diameter of the tool is around 200 micrometers. We perform a similar scratch experiment, but right now the milling tool is rotating. And we collect the data from this particular milling experiment with all these different sensors. So what you can see here is an acoustic emission tool. And here there are some thin film sensors. And under this particular bed, there are accelerometers and force sensors. And we are collecting all this data simultaneously. So whenever we are capturing these particular signals, when this cutting operation is happening, so what we want to see is, can we do a very similar analysis, get the frequency components out of the signals which we collected, and see and do a very similar analysis, extract features, and use the features to say predict my hardness, and see if that makes sense. See if we can actually predict hardness from these signals. So that's the basic idea. So right now, like immediately, if we look at this particular process, we find that it is rapid characterization. I didn't even remove this particular sample from my machine. So it has been printed here, and I'm milling it right here. I'm collecting the signals right here, and I'm trying to see if I can get anything from these signals. So that's the basic idea. So the samples which were printed here are high entropy alloys, cobalt, chromium, iron, and nickel. And these were finished initially using a 3/8-inch milling tool. And then we have a phase grinding tool within the machine itself, and a cloth polisher, which we use to finish the samples. So the samples which you see here, all these samples were finished on this particular machine tool itself. And then we have done this micromilling scratches, where we collect all these three sources of data. And so these are the material compositions, different elemental compositions, and we have like 8 different alloys. And for the current analysis, we just look at these 2 particular material systems, where if we just look at it, we can see a major difference in cobalt compositions and nickel compositions. 196C2 has like very low cobalt and very high nickel, and 196C3 has very high cobalt and very low nickel. So we took these 2 samples as our test samples, and the idea is, can we identify which sample is which just from data? So this is the case study. So this particular sample is 196C2, and this is a stitched SEM image. So what these orange lines are is the feed rate of my particular milling tool. So whenever I'm cutting this particular sample, the tool advances by 100 micrometers, and the spindle speed is kept at 2000 RPM, and the feed rate is around 48 inch per minute. So we calculate this first, and then we arrive at this, like around 130 micrometers per flute is how it's cutting. And we cut a depth of around 5 micrometers. And during these cutting operations, we collect all these 5 sensor data: accelerometer at 10 kilohertz, acoustic at 100 kilohertz, and we have a thin film strain sensor at 10 kilohertz. We have a high-speed camera which is running constantly at 250 frames per second, and a force sensor which is collecting data at 100 hertz. And the case study is like, we use data collected from the sample preparation and micromilling steps, and we want to train a model right now. So we want to know how the hardness values are changing across space. So we want to learn the spatial variation of material properties. That is what we are learning. And what we want to learn it from is the spatiotemporal sensor data. again, by spatial temporal sensor data, yeah, I'll be discussing in the next slide what spatio-temporal and how we can get that particular resolution from the experiments which we are doing. And why true is obtained from standard characterization procedures. Again, we need the ground truth at least for training this model. So for this particular experiment, we took the ground truth from micro hardness measurements. So again, as I said earlier, what is spatial and time resolution? So we look at this particular sample. Again, it was milled in these particular passes. So if we look at all these passes here, so each and every pass corresponds to a burst of signal here from acoustic emission. All these are acoustic emission signal. And if we look at this particular pass here, so just this one, so this particular pass is this particular signal. So this particular burst of signal is coming from this particular cut. So we completely identify where the cut has started and where the cut has ended. And we can go back and say, if I'm looking at this particular band, this is the signal where it's coming from. And this small square, which we are looking at, so this whole signal is from this end to this end. And this particular small section of data is exactly where this highlighted portion is. So what I'm trying to say here is we have spatial resolution. If I give a particular XY point, I can go back and exactly see where it corresponds to in the signal. I have spatial resolution where spatial resolution of 100 microns. So if you give me a point here and you say 100 microns from here, I want where the signal is, I can exactly show you which burst corresponds to that particular signal. And with respect to time, I also have the time series and I exactly know where the tool is on this particular path. So I have the spatial and time resolution with this synchronous data collection, which is happening. So that is important because when I look at my hardness measurement values, I again need to correlate this back to the hardness measurement values. And
Dr. Bhaskar?
Dr. Kumar, if I'm good. Yes.
Yeah, I have a question in this slide. Can I ask?
Yes. Yeah, sure. Go ahead.
Dr. Ravi Shankar. So whatever the highlighted area about red, there is no, I feel there is no cut there. Can you look into it? Because there is, the cut is there in the central portion because you have highlighted there. So the sensor signal normally whenever the milling cutter will be, see, you are emphasizing about only one milling cutting and which is at the central portion highlighted. So, but the highlighted portion of the red color, there is no cut. So, yeah.
You're saying this part, there is no cut?
Yeah, cut is there. Yeah, there is no cut.
Yes,
because,
so.
Yeah, the cut is there at the center.
No. Exact. Yeah, I'm sorry. Again, these particular samples. These
so the signal, as I guess, the signal, acoustic emission signal refers to each and every cutting edge interaction with respect to that when you are making this particular scratch. So my guess would be that you should have drawn the line horizontal, not the vertical. So particular segment are, yeah. So that's, I guess that's.
Yeah, I can give you the clarification. So the thing here is we have also collected the data from sample preparation, and this particular acoustic emission signal which we are looking here is from the macro milling sample. So this is from the 3/8. Oh, I'm really sorry. Okay.
Yeah, fine. Just I would like to say that, yeah.
Yeah, these particular data sets are from the 3/8-inch 6-flute carbide cutters and not from the actual micromilling samples. So the spatiotemporal resolution which I'm showing you here is the milling cut, the initial milling cut, which is actually happening with the 3/8-inch milling cutter throughout the whole sample. This particular case study, we still haven't looked at these micromill samples.
Yeah.
But right now, this particular data set refers to the 3/8-inch, where I'm finishing off the sample right after I establish a datum with my cutter. I use a very minor 5 micrometer depth, and I just finished the sample using the milling cutter itself. And so all these particular lines here, they refer to the the feed of the macro milling cuts. So we are not referring to the micro mills yet. Did I
Okay,
answer your
so
question?
yeah. The second I would like to say, so whenever you do your FFT analyzer, so you are changing from time domain to frequency domain. Yeah.
Yes.
So you're talking about surface finish. So can you comment about that the FFTs, the value of the, or it will move towards left side or right side of your, as the surface roughness improves, your FFT signals? This is the burst signal of acoustic emission. What my question
Ye-
is that if this assume that you are doing a machining with 5 microns depth of cut and 2 microns depth of cut, like so, if you decrease, automatically the surface roughness will go down, obviously. So now
Yes.
you take a burst signal for acoustic emission and which you convert into FFT analyzer. So in that circumstances, what will be your signal, whether it will move towards uh, datum, or I mean to say left side or higher side or lower side?
These are great questions, actually. Let me quickly answer. Bhaskar, I think I would like you to think through that too. First question is, how will it behave when you have very high finish on your surfaces? It would not go left or right, but the energy will actually come down. In fact, acoustic emission perhaps is the only one kind of a sensor that has the sensitivity to actually indicate some changes in the micro machining regime in those fine finish cut ranges, actually. If you look at the vibration data as well as force data, they probably will be just will be submerged within the noise bands. But acoustic emission luckily will be able to capture. But as you correctly said, the energy levels will be so low that you need some advanced processing to extract useful information out of acoustic emission. And also for to your earlier question, if you look at some of these central bands on the picture that you're seeing, what you're seeing are actually bursts that were coming out of the surface. So, so it actually looks like that because you are seeing the bursts and not the surface.
Yeah.
Anyway, I hope I answered some of your questions on acoustic emission.
Yes, sir. However, it is a fantastic, interesting work, though. So that's why we got a lot of doubts.
Oh,
Thank you.
absolutely. Thanks for your question.
Thank you, sir.
Bhaskar,
Thank you.
continue.
Yeah, please, Bhaskar.
Yeah.
Thanks.
Thank you, Dr. Shankar. Also, I would just like to clarify one single thing. So here we are looking, whenever we are doing the cuts, we are looking at samples which are less than 100 less than, yeah, we are looking at in the orders of tens of microns of surface finish. And again, the output which we are looking at is again not surface finish low. I kind of didn't mention it in the starting of my slides. So what we are looking at is whenever we are looking at these signals, if we can associate it with to the hardness of the material. So again, really interesting questions, Dr. Shankar, like with respect to like how the FFT response would change. I would definitely look back into it and see how the response would change. And also one thing I would like to add, as Dr. Bukkapatnam said, the energy levels would definitely decrease for all the sensors. But in terms of the shift, it is not just the process, but also the process and machine interactions which we get from these particular. I'm sorry.
Continue, Bhaskar.
Did someone have a question? Okay. So, yeah, the next part we would be discussing the feature extraction routine from the sensor signals which we have obtained from these passes. So now we have this particular milling pass where we got this data from, and we convert it into the FFT transform, and we get these frequencies. What the next step which we would do to extract our features? So we need a we need a set of x's. We need the feature vector developed to actually predict something. So here we slice this entire FFT into frequency bands of width of around 500 hertz. So what we do is we slice the entire FFT spectrum, and we add up all the energies in this particular bands. And whatever the cumulative energy in this particular band is, corresponds to this particular step here. So this is the cumulative energy which I have over my around 100 bands of frequencies, and this is my feature vector. I use this particular data as my feature, as my input vector X, and I want to classify which sample it came from. So right now we have 208 milling passes, which came from just these two samples. The first sample 196C2 and 196C3. And the dimensions of the input space, again, because we have 100 frequency bands and we have 208 samples, and the output is just binary. We want to predict if it is C2 or C3, that's it. And we have trained this particular data set with 3 different models. The first one is a basic logistic regression, and we have used a linear basis support vector machine, and we have also used a random forest classifier. In all these classifiers, we almost got a very high classification accuracy, and there's a reason for that, which we'll be looking in the next slide. And also, one more thing is we look at the variable importance, very similar to what we have looked in the nanolithography experiments. So looking at these variable importance plots, and again, going back to the process and understanding why these particular frequencies have played a major role in when classifying these 2 particular parts, that is still yet to be studied, and we are working on it. And to the part where why we got such like high classification accuracies. So wherever we did all these macro milling experiments, we also took some micro hardness measurements. So the micro mill here, which we did, served as a good identifier as to where we need to do these micro hardness measurements. And so whenever we did this, so this is a particular milling pass, and along the milling pass, I know where the band of this particular pass is, and because I know my feed rate, and I also know in which direction the mill is progressing. So I have all these different hardness measurement values which I've done, and this is the ground
Hello,
truth.
చెప్పండి. ఓకే, ఏమన్నారు సార్? మీరు టిల్ డేట్ వర్క్ అడిగితే ఇక్కడ 28 చెప్పారా మీరు? ఇక్కడ నేను జాయిన్ అయ్యాను.
Dr. Ajay, can you mute all the people? Yeah, I think Dr. Bhaskar, you can continue, please. Sorry for the disturbance.
Okay,
yeah,
no problem. So if we look at these again, if we look at these 2 samples, 196C2 and 196C3, so whenever we took these micro hardness measurements values, we saw that there is a considerable shift in hardness values for 196C3 with higher nickel content and much lower hardness for values where we have lower nickel content. And because of this discernible difference just from the hardness measurement values, we could kind of identify that, like, because a harder material when cut obviously emits higher vibrations, higher acoustic higher emissions in terms of acoustics. So whenever we have such proper difference in terms of hardness values for 196C2 and 196C3, we could identify that whenever we extract the features, the energy values would be very different, and we could get a really good classification accuracy. So the next step would be, now we can classify what sample it is just from looking at the sensor signals. But the next step is, can I actually predict my hardness values? So now I have the signals from all these which correspond to these particular hardness value measurements, and that's what we did next. So we broke the signal down into segments. We know what segment corresponds to what hardness value, and now we again did a very similar analysis. We built the random forest model and checked what we looked at the features, and now the feature set corresponds to a particular, this is a regression. So previously we saw a random forest classifier. Now we are looking at a regression model where I want to predict my hardness values. So the test accuracy of this particular model where I predict my hardness values was around 96.43. Again, this stems from the fact that the hardness values for these two particular materials are way off. And we can clearly see that from the signals which we obtain. And that is for material property correlation. So now so at the end of this case study, what we see is using these smart sensorized hybrid machine tool, what we can do is whatever we have achieved in nanolithography, we haven't achieved it completely with this particular milling experiment or the rapid characterization experiment yet. We still have a lot of things to establish for us to say for a fact that we can actually characterize the materials in a rapid fashion. But this is a starting step where we are seeing that from the sensor signals, we could see that we could estimate the hardness values and we can say that there is some discernible changes. So we still have a long way to go in terms of rapid characterization. So my next case study would be in terms of process monitoring using streaming image data. So until now, we have captured images, but we didn't actually look at the image data from these particular experiments. But what we are trying to explain here is the defect concentration in this. And so these are images from the Ti-64 sample itself. And what we want to identify here is the Bolling defects, which we are seeing here, which are gas-induced porosity. So which, yeah, in these particular samples, we see that suppose if we are looking this from a pure image standpoint, it is kind of difficult to exactly identify these anomalies. And we also want to track these anomalies in situ, like if you have some form of an imaging. So we want to kind of identify what's the porosity of these samples just from the images. So here we have these two conditions where the laser power has a very stark difference, and you want to identify these particular defects. These particular defects for identification, the problem gets particularly difficult because of the uncertainties in the location where these defects are present, and morphology. And also, whenever we are looking at these images, it is evident that there is a lot of noise and exposure differences at different points of this image. So, and again, if we are trying to build a model where we have these particular images and we want to correlate it to the porosity, so what we need is a lot of experiments. And unfortunately, we can't really afford that because like each and every experiment here is involves a lot of cost. And if we are going for supervised methods, the supervised methods are like actually infeasible because of the huge experimental costs which are involved. And we kind of need to find an efficient means to segment out all these anomalies. So this is work done by one of my outgoing seniors, which he has used a graph cuts based method where for any configuration, they determine the graph structure that minimizes the error in the measure of fit and the measure of smoothness. So by this, yeah, this is a segmentation algorithm. Like by using these, he came up with a comparison criteria for different unsupervised methods and supervised methods. So this particular score is a DICE score, so these are images from brain scans, and these are the areas which are to be identified in a patient with a particular ailment. So this is the expert segmentation which is there, and this is the estimated segmentation which comes from unsupervised learning models. And if we look at this particular DICE score, which gives the accuracy of the fit, so we see that this particular model which he has built, this is unsupervised, and we don't need any training samples for this particular method to work. So this unsupervised method performs like much better than most of these supervised models. And the current state of the art unsupervised methods have a dice score of around 0.3. And right now we are reporting somewhere around like 0.75. So this this very example, when applied to the examples which we have shown before, so these are the different defect segmentation results. We can see with all the other models from A to E that it has identified different areas of this as defect. This problem gets really difficult because of the differences in exposures at different parts of the image. It is just not black and white, and we can't use a basic thresholding technique to identify where the defects have occurred. And this is the particular method which we have developed, the unsupervised max flow, which shows an estimated this score of 70.56. So what we are showing here is a label-free, fast detection and tracking of defects without performing any additional data. And we don't actually need data sets to perform this particular defect segmentation. So let me summarize. We have discussed like 3 case studies, and Dr. Bukkapatnam gave a very high-level introduction of the 2 concepts of smart manufacturing, which we are actually targeting. We are using a smart, sensorized, hybrid manufacturing machine tool, and in conjunction with different AI techniques. So this whole setup is an enabler for different things. First thing is the concept of manufacturing as a service, the concept of materials on-demand manufacturing, where I not only get what part to manufacture, but also the part comes with particular specifications as to the properties which are required in the particular part. So we discussed how the materials on-demand manufacturing can be enabled using this particular machine tool. And we have discussed cases of rapid characterization of alloy systems in conjunction with AI and this particular machine tool, and autonomous material synthesis and discovery. So we are not at the discovery part yet, but we have looked at the synthesis part as to if we know the elemental compositions, and we can go to the hardness. Like if I want a particular hardness, can I come back and say like what are the different elemental compositions which are required? And finally, we have discussed a case study of the in situ process monitoring, where we have the final images from the parts which are ready for which are done characterizing, and if we can do some process monitoring from the results of what we get finally. So the central part is the hybrid manufacturing machine tool which we have here, and we are kind of using that to see if we can move forward and inch forward towards the autonomous material synthesis and discovery research. And that's my talk. Thank you. And if you have any questions, I'll be happy to take them. Thank you.
Yeah, thank you so much. Thank you so much, Professor Satish and Dr. Bhaskar. Now talk is open for any question. I request from the audience, if they have any specific question, they can directly ask to the speakers.
Yes.
Yeah. Any question from the audience? Yeah. I think if there is no more question, let us thank Professor Satish and Dr. Bhaskar for the wonderful talk. It was really a wonderful, you have covered the smart hybrid manufacturing rapid characterization, and you have presented the case studies which are very useful for the our students and who are doing research in this area. Thank you so much. Thank you so much, Professor Satish and Dr. Bhaskar.